Welcome back. So this is 11th lecture in this course on Bayesian modeling. My name is Himanshu, and in this lecture we are going to practice probability distributions in R. So R is a programming language, and I'm assuming that you know a little bit of R. If you don't, then please practice a little bit of R using R Studio before you start practicing with me in this lecture, right? So just to recap what we have done in previous 10 lectures is that we started with very basic idea of what is statistical inference, right? So whenever you are given some observations or data from an experiment which you want to analyze, right, you assume the fundamental assumption is this, that this data must come from some truth generative process, but you cannot directly access that truth generative process. You can only make some inference about the properties of the truth generative process, right? But how do we make those inferences? Well, we start with an assumption. Although we do not know what is the truth generative process, we assume that there is a probability assigner function f of theta which assigns real values to events in our event space, right? Those real values are called probability values, right? So this probability assigner function, which is called probability mass function in case of discrete sample space, and probability density function in case of continuous sample space. Okay. So this probability mass function or probability density function is our assumption that the data you are seeing might be coming from this particular probability mass function or probability density function. Okay. So we make this assumption, right? Now, one important thing that we discussed was that we never define this probability density function or probability mass function directly on our sample space. We rather define this probability assigner function on the values of the random variable. Okay. So, for every experiment whose, let's say, sample space is omega, okay. So, for every experiment with sample space omega, you first define a random variable x. Okay. Now, x, this random variable, is a function which maps your sample space to another space omega x, right? So, x, the random variable, is just a function. It takes values from your sample space and gives some real numeric value in another space omega x, right? So, whenever we define any probability assigner function f of theta, we define it on the values of the random variable. So, we define it on this space omega x, right? So, this function gives you probabilities of the events, right? Now, in this whole thing, we needed to understand what is exactly this probability density function, probability mass function f of theta, right? So, for which we understood three axioms of probability, because those are central to constrain exactly what kind of probability mass function, probability density function you can have, right? So, we had those three axioms of probability. And then we took some examples that what kind of probability assigner function you can have which would satisfy those three axioms of probability, as well as it would be reasonable to assume that what could be the truth generative process. Okay. So, whenever you have some observations, you need to think about two things, right? One, what could be the underlying generative process, right? So, for example, when you are doing a coin toss experiment, then it is reasonable to assume that underlying generative process could be a Bernoulli process. So, it could be a sequence of independent and identically distributed Bernoulli trials. Okay. So, all these outcomes are coming from a Bernoulli process. So, that is a reasonable assumption to make, right, rather than assuming that there is a Poisson process that underlies these coin tosses, right. So, you will always need a reasonable assumption which you think might underlie the data that has been generated in your experiment, right. Second, whatever probability assigner function you assume, it must satisfy three axioms of probability, right. So, that is how we make assumptions about the underlying generative process, right. And we saw some common examples which we often use to make assumptions about our data. So, for example, there was binomial distribution. So, these were cases of discrete random variable. A binomial distribution which would have a probability mass function. There was Poisson distribution which would have a probability mass function, then normal distribution for continuous cases, and it has certain properties that would be symmetric, would have two parameters, mean and standard deviation, and it also it would have a probability density function. Then we saw log normal distribution, which you can use if your data is not symmetric and it is it has heavy tails on the left hand side and the values are always positive. And then beta distribution, it's a distribution for continuous values between 0 and 1, right? So these were some common examples of probability distributions that we saw, because we use them very often for human experiment data, right? Now in the next couple of lectures, our goal would be to see that, well, until up to this point, everything we have been doing is before seeing any data, right? So you make this assumption about your experiment f of theta before seeing any data, right? So let's say you're planning an experiment, and that experiment would give you outcome xi in the ith trial. So you have already assumed that xi would come from f of theta. You don't know what is exactly the data, but based on some reasonable assumption that how xi could look like, you have already made an assumption that xi would come from f of theta. You haven't seen the data yet, okay? So in next couple of lectures, we would see that what would one do once you have seen the data. So once you know what is exactly this data point, okay? Because once you know the data, so let's say it turns out that your data, your experiment is producing three values, okay? So let's say x1 equals to 2, x2 equals to 4, and x3 equals to 1, okay? And let's say these are discrete values, and its experiment is about number of road accidents in a particular city in a day, okay? So now you have three data points, okay? So what you would do now? So let's say you assumed that xi comes from a Poisson distribution with underlying rate of road accidents lambda, okay? Now given these data points, so this is number of accidents on day 1, this is on day 2, this is on day 3. So given these data points, what you would do is this, that although you are assuming that these data are generated by a Poisson process, right? But you don't know what is the underlying value of lambda, which would generate exactly these data points, okay? So that's what we try to estimate. This is called parameter estimation. So given the data, we try to estimate what values of lambda would generate this data, okay? How do we do that? Well, it has different methods. So parameter estimation has different methods. You see these methods in frequentist inference, if you have done earlier, so where we estimate a point value of our parameter. In Bayesian framework, we never estimate a point value. I will tell you the reason why exactly that happens, right? So we will come back to this point later, but our goal would be to estimate what value of lambda, okay, would generate these data points x 1 to 3, which are basically 2, 4, 1, given that xi comes from Poisson lambda. So under the assumption that each data point comes from a Poisson process, what value of lambda would generate these values 2, 4, 1 would generate this data, right? So that's what we want to estimate. So basically want to estimate the true value of parameter lambda that would generate this data. So this parameter estimation is a crucial process in statistical inference, okay? So you need to estimate what value of the parameter must have generated this data under the assumption that data comes from a certain probability mass function or probability density function. For example, in this case, what value of lambda would have generated these data points 2, 4, 1 under the assumption that each data point comes from a Poisson process with underlying rate parameter lambda, okay? But the thing is that in Bayesian inference, in order to do this parameter estimation and going ahead with statistical inference, you need to now enter into computations. Now you cannot solve most of these problems analytically, right? So we'll need to do computations in order to do parameter estimation and later on to do basically statistical inference in the Bayesian framework. You will need computations, right? So now in order to do that, you will need to first understand that how to use these distributions in R. Okay, so you should be able to, for example, generate data from a binomial distribution. You should be able to compute probability mass for a particular value given a binomial distribution, right? Similarly, for Poisson and normal distribution, for example, you should be able to calculate probability density for a particular data point given a particular set of values or parameters, right? So you'll need to do all these computations, right? So that's why it is very critical that you use one of the programming language to do these further computations. So either you use Python or R, basically that's your choice. For teaching these lectures, I will be using R programming. So I'm assuming you are a little bit aware of R programming. If you are not, you should basically brush up your R, and then you can go ahead with next part of this lecture. Okay. So let me start with how to work with these probability distributions in R. Okay. So let us begin with the binomial distribution. Okay. So I hope you're aware of this RStudio interface. So basically here in this portion, we will write our code. So basically this is the editor of the R interface. This part is the compiler, so it would show you output. So code as well as the output that you will write. This part shows you some basically your variables that you would have defined here, right? So all the variables would show up here, and this part would show you plots and files and other things, right? So we will be writing our code in this portion on this top left hand side box, right? So let us work with the binomial distribution. So first thing we need to know is that how to generate random values from a binomial distribution. Why this is useful? Because this is exactly the kind of thing you would do in order to generate predictions from a model. Okay, so let us assume that a participant is doing a task where the participant has to recognize whether the word shown on a screen is a meaningful word or not. Okay, so they will make a response whether the string they are seeing is a meaningful word or not. So what kind of response they will be making? They will be making a yes or no response, right? So either it's a word or a non-word, right? But their response could be either correct or incorrect, right? So they can make either a correct response or incorrect response. Okay, so it's a binary response. Okay, in a particular trial. Okay, now suppose in this experiment you have 50 trials. Okay, so you will give the participant 50 strings, and the participant has to recognize whether it's a word or not word 50 times, right? So out of these 50 trials, it could be the case that participant would give correct response in 45 trials. So out of 50 trials, the participant gives correct response in 45 trials. Okay, so something like this could happen. Okay, now suppose you already know the true generative process, right? What does that mean? So you already know that the number of correct responses, okay, number of correct responses in this experiment comes from a binomial distribution. Okay, so far whatever I'm writing, these are all comments. I'm just writing text here. Okay, so I'm not writing any code so far. Okay, so let's say you already know that the number of correct responses comes from a binomial distribution with sample size 50. So total number of trials, this is n, variable n in the PMF of binomial distribution, and underlying probability of success. So underlying probability of correct response in any trial is, let's say, 0.9. Okay. So underlying probability of producing a correct response is 0.9 and total number of trials is 50. So you already know the underlying generative process because you already know the true value of underlying probability of correct response. Okay. Once you know the underlying generative process, although it never happens, right? In reality, you never know what is the true generative process, right? But hypothetically, let's say you know that this is the true generative process, right? Then what kind of data you can expect in a particular experiment, okay? So that's what we are trying to do here. So this is called generating random values from a distribution where you already know the true values of the parameters, right? So let's see what kind of data you would generate if you already know the true generative process, which is a binomial distribution with probability of correct response 0.9. Okay. So we will call it xsim, basically simulated data, right? Now the function we will use to generate random values from a binomial distribution is rbinom. Okay. So binom stands for binomial distribution, R stands for generating random values. Okay. So we are drawing random values from a binomial distribution. Okay. How many experiments you want to simulate? Let's say you want to simulate only one experiment. You know the true generative process and you want to simulate what will happen if I do this experiment next, right, on a particular participant, right? So the simulated, so this is what you should do. So n1 is basically the number of samples you want to draw. Okay. So number of experiments you want to simulate. Size is 50. So total 50 trials are there. Theta is, basically it does not define it as theta, probe. So there is parameter probe. So theta parameter is called probe here. So probe is 0.9. Okay. So I have given the probability of success 0.9, number of trials 50, n equals to 1 means I just want to simulate one experiment. I want to simulate how many correct trials would be there in a single experiment with 50 trials, right? And let's see what happens. So I have basically now executed this line of code and let's see what is the output. What is xsim? Okay. So xsim is actually 43. So it is showing on this side. I don't know if I can take the console on this side. So whatever is comfortable for you. So it is showing the output on this side. Okay. So because the console is on this side. So I think this is better for readability. Okay. So once I executed, I see this output. So it gave me 43. Okay. So there were 50 trials in this experiment. I knew the true probability of correct response, which was 0.9, and I simulated a random experiment. Basically, let's say I called a participant and I asked participant to do this task, and this is the output I got. Okay. Now the interesting thing is this, that although you know that the exact probability of correct response is 0.9, okay, then why the correct number of response is not 45? Okay, because if you multiply this 0.9 with the number of trials 50, you get 45. So if this process has to be totally deterministic, right, then the number of correct response should be 45 because the probability is 0.9 and total number of trials is 50. So you should get 45 correct responses, right? But that's not how it works, right? Why? The reason lies in the fact that this is a generative process, right? What does that mean? That this is a probability assigner function. So even when you know that the true probability of correct response is 0.9, so basically you know the theta now, right? So theta is 0.9, number of trials n is 50, okay? Even then, the probabilities assigned to different outcomes, right, different possible outcomes, is a distribution, right? So although the probability of obtaining an outcome like 45 correct responses, so probability of obtaining 45 correct responses is highest, but there is still some probability of obtaining responses like 44, 43, 46, 47, right? And that's how the probability mass function works, right? So if you draw the probability mass function of a binomial distribution, looks like this. You know the PMF of binomial distribution, right? F of x and theta is given by n chooses x, theta to the power x, 1 minus theta to the power n minus x. So although you know n is 50 and theta is 0.9, right? If you plug in these values here, then it becomes a function of x, right? So you know n, so 50 cx, theta is 0.9. So let me say 9 by 10 to the power x, 1 by 10 to the power 50 minus x. So now this has become a function of x. And what kind of function exactly? Now x can take only discrete values, right? So the function is like this. On x-axis, you would have values like 45, 46. These are number of correct responses. 47, right? 44, 43, 42, and so on. So at 45, you would indeed have maximum probability, but you would have some probability value at 44, 43, 42, although lower probability, but you would have some probability value. What does that mean? It means that although 45 is most likely to be generated by this generative process, but these values 44, 43, these are also likely to be generated from this generative process, although less likely than 45, but they are still likely to be generated. Okay, and that is what is the point, because it's a random generative process. So it would generate random values. So there will always be some randomness in this process. Okay, so there will always be some randomness in the process. So even though you know the exact probability of producing correct response is 0.9, that does not mean you will get correct response 90% of the times. In the actual output, you might even get, let's say, just 30 correct responses out of 50 trials because of the randomness, right? So do not really know what you are going to get in the next experiment. You can only have an idea of the distribution. Okay, what does that mean? That if you, let's say, simulate thousands of experiment, if you do this experiment 1,000 times and then you draw the histogram of what kind of responses, what is the number of correct responses you got, if you draw a histogram of that, then you roughly get the same distribution as the probability mass function. Okay, let me show you how. So this here we just simulated one experiment. Okay, now let us simulate a lot of experiments. Okay, but before going into that, let me show you what happens if you run the same line of code again. That means you are simulating another experiment. This time you get 49. See, so the randomness, because of randomness, changes, right? So you can get any output, because 49 would also have some probability mass. So it is likely that 49 can be generated, although low likelihood, but it can be generated. See again, 43, 45, 47. I'm just running the same piece of code again and again. 47, 44, okay, 47. Yeah. So every time you get a different response, right? Now let us, rather than simulating one experiment, let us simulate 10,000 experiments. So what will happen if you know this is the true generative process and you do this experiment 10,000 times? Okay, so let us see what would happen now. So now your xsim would be a vector of basically 10,000 values. Okay, let us draw a histogram of these simulated data points. So this is how the histogram looks like. See? So actually this is slightly misleading. So let me just draw a discrete histogram. It's all these data points are discrete, right? So you cannot get anything between 45 and 44. So let me see if I can induce breaks here. Okay, yes, I think I can induce breaks. So let me induce breaks from 35 to 50. I'll have to take a look that how to induce breaks. I want to discretely plot each value. I think there should be another way. So maybe I will use the plot function. Oh, this is different. Okay, fine. Anyway, so we can do that later. But the point to be noted here is this, that if I simulate such 10,000 experiments, then you see this is the number of experiments here. So around 2000 experiments are in this range. So basically you would either get a 44 or 45 or 46. So these values, these are the number of correct responses. So in around 2000 experiments, you get this number. Now in around 1500 experiments, you get a number like 43, 47, right? And this keeps on decreasing, right? And you get basically no experiment which has number of correct responses less than 35, because that is rare. Because the probability mass function you would have, it would assign a very low probability to obtaining an outcome less than 35, right? So this graph actually mimics the probability mass function of a binomial distribution with underlying probability of success 0.9 and number of trials 50. Okay. What will happen? What would change in this graph if, let's say, the underlying probability is 0.5? What would happen now? So let's say you have a fair coin and you're tossing the coin 50 times and you're counting the number of heads. Okay. Let's see what happens. This is what you see. Okay. So because you're tossing it 50 times and the probability of success is 0.5, the most of the probability mass is near 25. Okay, so you are very likely to get a response. You are very likely to get 24 heads or 25 heads or 26 heads. Less likely to get, let's say, 22 and 28 heads. And almost unlikely to get less than 15 heads or more than 35 heads, right? So in fact, the probability mass function would look similar if you draw the probability mass function. Do you want to draw the probability mass function? So we can actually draw the probability mass function as well. How? So actually the function, there is a function in R that you can use to calculate a value of a probability mass function, probability density function. So for example, in order to calculate probability mass, you can use this function d binom. Okay. How do we use this? So let's say you first create a vector of values of your random variable. So let's say vector of values I need are from 10 to 40. Okay. Now for each value of this random variable, I want to calculate probability mass given that underlying probability is 0.5 and the sample size number of trials is 50, right? So this will be called probability, right? So for each value of x, I've calculated its probability given that these are coming from a binomial distribution with these parameters, right? Now I can plot x versus these probabilities. Okay, so this is the probability mass function. See, okay, so each dot is representing the corresponding probability mass corresponding to a particular value of the random variable. Right? So this is the graph of the probability mass function of a binomial distribution where the underlying probability of success is 0.5, right? And you get exactly same distribution of the data, right, in the previous graph. because you generated from the same distribution and you generated 10,000 experiments, right? So if you draw the histogram, it would look same as the probability mass function. Okay. All right, so I will continue from here in the next lecture, and we'll see more such examples, that how to generate from different probability distributions and how to calculate these probability densities and probability mass given a particular probability distribution. All right, thank you very much. We will meet in lecture 12.